let's see, I have to have somebody else. Sir, would you help me out here? Dig deep in there. Dig deep in there. Pull one out. Okay, let's see. Oh boy, Elaine Crutchley. I think she was one of the speakers with. Yeah, but she's not here, so she's not eligible. Is she outside?
Yeah.
Chris, can you look and see? I don't think so. I think she left. If she left, she's not eligible. You have to be here. That's my rule. It's my game. I make the rules.
Make the rules.
Thank you, sir. Hang on, let's just make sure maybe she came back. Then I have a real problem. We have two people. How would we solve
You'd
that?
have to buy a second one.
Huh? Oh, she is here. Elaine, you won. Yeah, congratulations. Thank you. Yeah, thank you for your presentation. Yeah. I had thought that we had left.
Oh, no, we're just out there.
Yeah.
Everyone else is not sure.
Yeah. All right, well, congratulations. All right. So now we have my friend Andrew Weekley, who is going to give a presentation on acquiring weather data, which is actually quite an extensive endeavor.
It is. How do I get my presentation? Mike?
Yeah.
So I'm assuming folks here are not familiar with numerical weather prediction data. Is that an accurate assumption? Any atmospheric scientists in the room? Oh, awesome. So the amount of data that's available through NOAA is remarkable. Basically, the weather forecasts that have been run for multiple numbers of years are available through the NOMAD's NCD web service. And so, for instance, if you're building a machine learning algorithm that you want to, say, for instance, predict what ski area you want to go to, this might be a valuable data set to consider in your machine learning algorithm. Just a quick note on terminology. So models are run on a regularly scheduled basis. So for instance, when you watch the news at night and you have the weather forecast being presented by the person, this is being based upon models that are run, say for instance, every 6 or so hours. And so you have a model run time at say 0Z, and you have a forecast time, say out at 1 hour in the future, 2 hours in the future, 3 hours in the future, that kind of thing. And there's a large number of models that are available, and they each have their own assumptions and their own specific packages that have gone into to build that. And so when you go and you look at this Nomad's web page, you will see all these models there, and you will see that for instance, you'll see the NAM, and you'll see the GFS, and they'll all have their different domains, and they'll all have different data sets that are available in them. And so you want to allow yourself the time to go through and really look at that. It'll take about a day just to sort of sort through to see what's available, at least. And again, there's, myself, I'm not an atmospheric scientist, and so when I look at these, the data that's available in these models, it to me is, wow, oh gosh, what is this thing? But the information is there in terms of when you go in and read the file formats, you can see that there is details on what the field is. So files come in either the GRIB or NetCDF format. Are folks familiar with GRIB or NetCDF? HDF formats at all? Okay, so GRIB is just, it's very specific to the numerical weather prediction community. It's binary file format. It's a hierarchical, semi-structured data format. But there are tools available. For instance, I use Matlab to load in the GRIB data, and you can create a data structure, and it has all the attribute data with it that describes, for instance, the different fields and what the units are and things like that. So there's a lot of information that's available just within the file itself. And then another thing I wanted to mention too was, so for instance, when you're dealing with a numerical weather prediction file, the models themselves actually can be run in any number of ways. And one way that actually you can do your modeling is, instead of doing, say, altitude above ground, you actually want to model it, say, at constant pressure. So for instance, you could load in your model data and you look at it and you say, gosh, my variable in the y direction or in the z direction is pressure. What is this? Well, it's because it's better to model your data at constant pressure than constant altitude. So oftentimes you'll have to go back and you'll have to find, what is the height associated with that pressure? Because here you have a flat pressure, but the actual altitude is changing. So when you want to go in and say, for instance, you want to find, some variable, say the temperature at a height, like say, for instance, the top of Winter Park, you're looking at the temperature field, but that's in pressure levels, you're going to need to go and you're going to need to dereference it and figure out what actual altitude that data point is. So that's just sort of one thing to be sort of aware of when you're working with these data sets, that you go and you look at the attributes, you see what the different dimensions are, and that you may actually have to go and look at other fields in the hierarchical data format in order to get the actual XYZ position that you want. So I have here an example of, I extracted data from the HER model, which is the high resolution rapid refresh model. And I was using experimental data set, the experimental model. And so a lot of these models are actually run operationally. And so you can go out and you can download the current weather forecast for right now if you wanted to. And then of course there's the operational data models, and then there's experimental models. And so I just have here some simple Matlab code. All I'm doing here is I'm converting my GRIB file, which I've actually already converted to an HDF5 file, into an internal data structure. And then I'm building a projection for the mapping toolbox. And then I'm converting my projected, so this particular variable that I'm looking at is in projected space. So are there GIS folks in the room? Sort of. Okay, so you have what you need to do is oopsie. You go in and look at the attributes of this particular data field. And so, for instance, this particular data field is in the Lambert standard map projection, and I know I need to specify my geoid. In here, it's just the radius of the Earth in kilometers. And again, these are attributes that you can find in the data in the actual NetCDF file. You just go and look at the particular field, and it will say, this is, Lambert. Here's the origin of the field, and then when you dereference, the XYZ or the XY of your map in your projected space, you can then use an inverse transformation to get your latitude and longitude out. And then, of course, this is just code here to plot it. And so here I have this example of what we're looking at is the precipitable water for the entire atmosphere. I believe the units are in centimeters. And so, for instance, you have 60 centimeters of water here, down in the Gulf. And this I took from, I think it was December 21st of 2014, and we had a really big snowstorm that day because I looked at the SNOTEL sensors, and one of the SNOTEL sensors was registering 1.5 inches of snow, which I thought was really interesting because here you're seeing very little precipitable water over Colorado. And then one thing I also wanted to mention was that, so I used to work at the National Center for Atmospheric Research in the Research Applications Laboratory. And one of the products that they had developed there was, they have actually a fairly large project on road weather. And they actually do have, I was looking at their webpage just the other day, and they have a product that they're developing for the Colorado Department of Transportation, which is forecasting travel times on I-70. And they're taking an approach probably where they're leveraging weather forecast data to come up with those forecasts. And then of course there's the SNOTEL sensor network. Are folks familiar with this at all? Any backcountry skiers in the room? SNOTEL is really quite remarkable. So all across basically the West, there are snow stations with basically measuring snowfall. And what these are actually in place for is to do watershed management. So in order to estimate how much water is going to be available. But this is a really great data set if you're trying to come up with a ski prediction algorithm. And so I wanted to draw attention to that. And I think that's my last slide. So any questions? No? Great. Well, enjoy.
Hey, you think it's okay to get the print or was that right after? So thanks for hanging in there with me. Getting close to the end here. My name is Chris McHenry, and I'm going to present on Azure Machine Learning. I think the real value of machine learning is going to be realized when we enable us humans to discover hidden insights from our data and hopefully make better decisions. And I think the way to do that is to embed machine learning in our applications. And that spans from our entire line of business applications like ERP and CRM, all the way to consumer mobile applications like we're talking about for the hack ski competition, enabling us to drive less and ski more. I'm all about that. So today I'm just going to give you a quick intro to Azure Machine Learning. Talk about some of the use cases that you could use Azure ML for in your data science projects. Give you a hands-on demo of Azure ML, hopefully convince you it's fairly easy to get started with, and how you can operationalize your models with Azure ML, and then just how to get started. So why would you be interested in Azure ML? Well, as I mentioned, it's super easy to get started with it. You don't have to go out and buy hardware, software. It's in the cloud. You access it through a browser entirely. And you can also bring your existing R and Python code directly into Azure ML and use it largely unchanged in Azure ML. You get that benefit of one-click publishing for your models, so it can be operationalized and consumed by various applications, software applications. And since it's cloud-based, you're only going to use what you need. As a machine learning practitioner, what are some of the use cases for Azure ML? Well, first of all, you can build a data pipeline to do your data cleansing and pre-processing right in Azure ML, so you don't have to have a pre-step that doesn't integrate with your model building. But then, presumably, once you get your data built, you can convert that into a model and evaluate and compare various alternatives and select the best model. So once you've got a good model that you're happy with, it's easy to operationalize that, as I indicated earlier. Another great benefit is you can kind of mash up your technology. So if you're using R and you have some good R algorithms for machine learning, you can combine that with Python directly inline in your experiments. And then lastly here, there's newly added support for Jupyter notebooks, if anybody's familiar with those. It's a great way to do data exploration, share that, create reproducible research, and share the results of your machine learning models with others on your team. So it's a great way to document your efforts. So if you don't know, Azure's Microsoft Cloud service, and they provide some out-of-the-box algorithms. They're world-class, they claim, algorithms. I'm not an expert enough to tell you if that's the case or not, but they provide some good out-of-the-box algorithms for things like anomaly detection, clustering. There's various options for two-class and multi-class classification and regression. So for someone like me, I come from a development background. I'm not a data scientist. And for someone like me, it's a great way to get started. For data scientists, it might be a good way to benchmark your own algorithms against some of the work that Microsoft's provided right in Azure ML. If that doesn't work for you, again, you can build custom algorithms with R and Python. There's kind of two flavors of this. You can use the execute R or execute Python module to do your data processing and cleanup. And you can also build models with that, but you're responsible for kind of taking care of saving off your model, and then at the time you want to use it for prediction, accessing it. So this create model module for R enables you to do that and takes some of that heavy lifting off you as a machine learning developer. Python support for that kind of thing is coming in the future. So I want to jump over and do a quick live demo, and I'm really hoping you can read some of this of Azure ML. So I'm logged into my workspace right now through my web browser. I'm using Safari, so it doesn't require IE or anything like that. And I have a list of my machine learning experiments here that I'm working on. And these are basically, as I indicated, simply a data flow that you can leverage to build your machine learning models. So I'm going to open up one of these. Actually, I'm going to show you how to create a new one. There's some nice samples out of the box that you can leverage. I think there's one down here for flight delays, binary classification of flight delays. Might be good for the hack ski competition as a good start. Right here it is. So it's kind of the same flavor of what you're looking at for that. So it's really easy to get started building an experiment. You can pull in these samples. There's also a gallery where you can get the work of others and pull it into your workspace, modify it, hopefully publish it back out for the community to use. And I have some pre-built experiments I want to take a quick look at. I've got this automobile price prediction. It's one of the samples that they provide with Azure ML. They also provide a lot of the data sets from the UCI machine learning catalog, if you're familiar with that. So you can just pull those right in and start experimenting with the tool. So here I've got the automobile price prediction. So I make that a little bit bigger. Hopefully that's better for you. So I have a data set, and the nice thing about this too is you can kind of quickly visualize it and explore the data a bit right in line in Azure ML. So here we've got a sample of our columns. Shows you how many rows and columns you have in your data set. And you can select the individual columns, for instance. Let's take a look at the miles per gallon, highway miles per gallon. And over on the right, it gives you some high-level statistics about the distribution of your data set in that column. It even gives you a histogram down here. You can use that to compare against different variables. So let's say I want to compare the highway miles per gallon to my price, and it generates a nice scatter plot. We can see they're kind of inversely correlated there. So it's a really cool way to just get a quick visualization of your data. You can also use box plots here if you prefer those over the histogram. So you can view your numerical values as a box plot. So a good way to get in, visualize your data. And then there are some out-of-the-box modules where you can do data pre-processing. For instance, I've got this project columns here, and I can deselect one of the columns that I don't want to use in my analysis. There's some modules that enable you to scrub out missing values, and then we want to select back in some columns. There's a split data module that enables you to split your data into a test and training data set. And so what I'm doing here is actually comparing two different algorithms. These are out-of-the-box algorithms. linear regression and our boosted decision tree regression algorithm. And I'm going to feed my data set into the training module and references algorithms, and then I'm going to feed my test set into the evaluate or the score module and see how well the test data set does on my model that I've just trained. Okay, so if we visualize the output of one of these score models here, get it here, it will add a label or a prediction for a price. So here we've got our scored labels, and we could compare those, for instance, to the labeled price that we provided in our data set. You can see there's a pretty good positive correlation in my test data set. So that's a good thing for me so far. And then we've got, we can feed those two scored results into an evaluate module that kind of shows us which model is performing better. So it gives us some of that high-level error information, statistics, and coefficient of determination, and then gives us a histogram of our error. So it's a nice way to take and combine different models on the same data set and evaluate which one's working better. That's a quick intro to experiments. Once you've created an experiment, what you actually do through one click is you set up a web service, and it'll store off your model as a saved model in this little kind of cubic square here. The saved models will show up. And so I've got a couple saved models here. I've already saved off the automobile price prediction. And I can leverage those in my web services that I publish with one click. So I take those, my training experiment, Azure ML will create what's called a prediction experiment. I'm going to walk through this in a minute. And it'll save off your model, and it'll generate in one step a web service that can be invoked by various applications. Okay. So we'll go through that in a little bit more detail in a sec here. Another thing that I mentioned quickly was the support for Jupyter notebooks. Is anybody familiar or using Jupyter notebooks? Okay, so a lot of people are interested in this. Jupyter notebooks, if you don't know, are a way to combine your markdown and code to kind of document things, and it takes a minute for it to come up here. So you can have executable code in line. So for Azure ML, if you build a model, this might be a great way to document your model. Might be a great way to communicate with your team, your data exploration. This is why I chose these features in my data set, that kind of thing. So you can combine that markdown here. We have different code blocks and markdown blocks. Right here I've got a code block that generates a graph. So for instance, I could shift enter and execute that right in line. So it's kind of executable documentation is the way I think of it. So it's a pretty cool new feature. I encourage you to check it out. Lastly, I just want to hit on the settings, and as I mentioned, we're in our workspace, and the settings, I'm running a free workspace, by the way. I'm going to touch on that. There's a free tier that you can use for as long as you want. Gives you a lot of power right out of the box to do most of the things you really want to do, especially to validate the service. So they do limit the storage here, and I'm limited to 10 gigabytes. And I've used only a fraction of it right now, so there's some limitations to that free tier. Another thing that's kind of cool is your workspace is entirely programmable. So there's an R package that you can use to call your workspace, publish experiments, retrain models, things of that nature. Anything you can do in this UI, you can pretty much do through some R code directly and program that, set it up as a script, and you use these authorization tokens to gain access to your workspace. You can also delegate your workspace out to other users. All they need is a Microsoft Live ID, and they can come in and collaborate on your workspace. So that's kind of a high-level tour of the studio environment, your workspace for machine learning applications. I want to drill a little bit deeper into a particular experiment here and give you a flavor of some of the things you can do. So this is using, I think this data set comes from the UCI catalog also. It's for breast cancer patients and predicting the recurrence of breast cancer. And so if we visualize that real quickly here, we've got a number of features and then a label class, whether the patient's likely to have a recurrence of breast cancer. And these features are all normalized across a scale of 1 to 10. Okay? So we have a pretty simple experiment set up here where we're just splitting the data directly. Our data set's already kind of pre-formatted for us, and we're just splitting the data set into a training and test data set. And then in this case, rather than use the out-of-the-box models, we're going to build our own model using our code. And so Azure ML provides a lot of packages that are in CRAN. If you're an R user, you're familiar with CRAN. A lot of those are provided out of the box with Azure ML, and you don't need to do any additional work. If there's actually something that's not in CRAN that you want to use in Azure ML, you can import it as a zip file in your data set and feed it into your trained model. So you can either leverage your code or other packages that don't exist in Azure ML that way. So with this create our model module, what we're going to do is actually leverage the E1071, which is a collection of machine learning algorithms. And we're going to use naive Bayes to do some classification on our data set. And so we just basically, Azure ML is going to hand us a data set that is fed into this module, and we'll do some pre-processing to get the data shaped the way we want it to using our code. And then we're going to feed it into the naive Bayes function that will train a model. Okay, so we're training the model, and the output we're providing is a model. So Azure ML is going to take that model and save it off for us. And that's where I was talking about some of that heavy lifting of integrating, saving off your model. If you use this create R module, or R model module, sorry, tongue twister, it's a nice way, convenient way to interact with your models and save them off for use in various web services. All right, you also provide a scoring script here as well, and it's also using the same package, but it uses the predict function here. And the output data set is the scores and categories assigned to your prediction, the data that you're trying to predict. So you have kind of two scripts that you provide to the create R model, and you feed that into your out-of-the-box train model, and finally you're going to score that. And at the end here, what I wanted to show with this particular experiment is we're kind of doing that mashup of combining R and Python. We're not going to use the out-of-the-box evaluate module. We're going to use some Python code that we have to do that. And it's going to generate some of the confusion matrix data for us and also create an ROC plot. So, oops, sorry about that. Give me 1 second to get back there. So we're mixing our Python code to do the evaluation with the R code to do a model. And what it's going to output is actually our probabilities and, or I'm sorry, our confusion matrix statistics here on the left-hand side. So if we visualize that, you have your accuracy, precision, recall area under the curve. Our model looks pretty good. And then on the right-hand side, it actually takes any of the standard out that you produce with your Python script and puts it out into a nice interface here where you can visualize the data. And you can even feed that into a Jupyter notebook if you want to. There's a, I don't know if you saw it here, but when you right-click, there's a open in a notebook. So you can save off the results of this to a Jupyter notebook if you'd like to. So it's pretty cool. With one click, or with a few modules here, we can do a lot of combination of R and Python. With one click, however, we can create what's called a predictive experiment. So Azure ML then looks at this experiment and finds the key parts that you want to use in a prediction scenario. So we're using it in a training scenario here. In a prediction scenario, you're going to pass in some new data, unseen data, without labels, and you're going to want to get results. What is the predicted label and what is the probability of that prediction? And so that's what the predictive experiment does. And as I said, Azure ML generates that for you with one click. On the left here, we have our stored model. So if we click on it, you'll notice it doesn't have any of that R script that we were working on a bit ago. And we also have our data set fed into our score model module. That's to provide the web services with a schema for the input and output of our data set. So we basically just take a web service input, we pass it to score model, and an output comes out that has our label and our probability of matching that particular category. So if we visualize, or actually I'm not going to visualize that right now, I'm going to show you through the web services interface, but down here at the very bottom, there's a button that you can click on to deploy it as a web service. And once you have it out as a web service, I've already done this, so I'm going to just quickly jump into it. Once you have it out there as a web service, you can open up a documentation page that allows you to test the web service right in line, so you don't need to write any code to test it. It gives you an API key that you can provide to developers to embed this in applications. There's also a request response and a batch execution, so you can do one at a time, one prediction at a time, or you can do a batch execution where you feed in a batch and get a bunch of results back. So I'm going to do a quick test, show you how that works. So it generates a nice little GUI for me. I can put some sample data in here. I'm just going to put a bunch of 2s in real quick. Show you how this works. So again, this is all kind of scaled data from 1 to 10, so it's pretty easy to demo this. So 2 is a low result on all these variables. So if we run that, it fires off down here in my corner here. It's going to fire off. You can't see the result very easily on where you're sitting, but it shows you the results, your input data, and your predicted label, which in this case is 0. The patient's not likely to recur. And the probability, which is a very, very low number, to the -8, so very low probability that patient's going to recur. So you can test your service in line with Azure ML. There's also documentation pages you can provide to a developer, and those give you the endpoint that the developer needs to call to access this model, all the inputs, request headers. You'll notice this is JSON data, so it's RESTful web service. So the format of the JSON's content that they need to pass in the request, and what the output's going to look like. And if you've documented your model sufficiently, there will also be data definition for the inputs and output variables. Then finally, down at the bottom, there's a set of sample code. So we've got sample code generated for C#, Python, and R that you can copy and paste into your project directly and start using this straight away. If you're not using one of these languages, you can use the documentation. Almost all languages can talk to JSON these days, RESTful web services. So it's pretty easy to integrate this into your existing software. All right, so that was a pretty whirlwind tour of Azure ML. Hopefully you saw it's fairly easy to build a machine learning model, get it out there so it can be used by other applications. I'm going to jump back to the PowerPoint for just a second here and finish up. So if you're interested in getting started, it's super easy. You go to this website, https://studio.azureml.net, and all you need is a Microsoft Live ID. You click the Getting Started link there in the center of the page, the blue link. And if you don't have a Live ID, you can create one on the fly. You can use your own email address, which is what I would recommend. You create your Live ID, and it creates you a free workspace, and you can go to town, have fun with it. Some of the trade-offs, free versus standard. There aren't too many in my mind, especially for just determining if you want to use this service at all. It's, you can do most of what you need to do for the free tier. You don't need a credit card for the free tier. When you go to the standard tier, you need an Azure subscription, so that requires you to put in a credit card. I would recommend also, if you're considering actually using this in production, that you create your free workspace with the login, the Microsoft Live ID that you're going to use for your Azure subscription if you don't already have one. If you already have one, use that same ID, because what it enables you to do is copy and paste your experiments between the free workspace and a paid workspace. You're limited to the number of modules per experiment, so you can build a pretty complex experiment, with 100 modules. Your max duration of your experiment, so if you go over an hour, they kind of cut you off, and you're limited to 10 gigabytes, like I talked about. Also, you can't scale your service out. It's a single node. It's on the staging web API, and there's no SLA with it. So you get a lot of capability for the free tier, definitely to get started, and you can probably cover a lot of ground in your applications with that. So this is my contact information. I put stuff out about Azure ML. I'm working on some training courses and whatnot if you're interested. Hopefully I've convinced you that we need to get machine learning into our software applications, and Azure ML is a great, easy way to do that. And so have fun with it. Thank you. Does anybody have any questions? Yeah.
So is the free version, kind of the teaser version, is that limited to personal use, or can that be used for commercial use as well?
I don't know of any restrictions around it. So I believe, they discourage you from using it in production applications, but I don't know practically if there's any reason you can't do that.
Well, no, I mean, it's just more like, if you wanted to estimate a model, use it for somewhere else,
Yeah.
do benchmarking.
Yeah, definitely you can do benchmarking, explore the tool with it as much as you want. My understanding is it'll be available forever. It's not like a time-limited thing as well either. They've said publicly that we're not planning to discontinue this sometime. Sometimes Microsoft can do that, but in this case they say they're not going to.
They have BizSpark, so if you're building a product, like not consulting, but if you're building a service or product, they'll give you a whole bunch of it for free.
Yeah, $200 worth of credits per month you get free for 3 years with BizSpark. I signed up for it. I would, if you want to do anything or just play around with it, sign up for it and go ahead.
That UI where you just have those modules together, I mean, a lot of them were pretty simple things like, the linear regression. Was it as simple as it looks? Could I just drag? Was it just like a drag and drop UI?
Absolutely, it's just drag and drop, and I didn't really cover a lot of the modules. I didn't want to spend a lot of time on it, but there's all those modules I showed up on the graph with, anomaly detection, two-class classification. All those are available right there on the left-hand side. There's also a lot of modules for data processing, mathematics, statistics that you can use right in line. So you can either code that up in R if you want to, or Python. I'm more of an R. I can't tell, but you can use R and Python to do that data processing and cleaning inline, or you can use the out-of-the-box modules to save you a little bit of time.
And for the modules that you drag and drop, can you kind of see the fence what they're doing?
No, those are completely black box to you. One of the things I like about Azure ML is that the whole thing's not black box, so you can control it as much as you want. You just have to be ready to write some code yourself, So that's not the point of it. I think Microsoft, they feel like those are proprietary algorithms, whatever the case might be, so they don't give you access to the code for that. Yeah.
So I'm assuming you could write as complex of our code as you wanted and make a module.
Absolutely, yeah.
Okay.
You can even save your R code off as a reusable module that you don't have to recode every time. So you can save it in your workspace and then reuse that same. There's a, if I open up an experiment here, I can show you that. There's a, down at the bottom, there's a, well, I'm not exactly sure what it is. There's a saved model, or I'm sorry, a saved module. So you can take your R code and save it off as a saved module and then reuse that module across multiple experiments.
So I assume you'd have to write it properly though, so that you've got inputs, the R code treats them properly, and outputs and all that.
Yeah, there's a contract effectively you're working with. You have to adhere to that contract, and then within the body of your code, you can do whatever you need to do.
Yeah, thanks. Okay.
How expensive is the service beyond the free tier?
Yeah, good question. So I do have a backup slide for that, I think. So here's the way, it's not cheap in my mind, especially if you're doing, we have an email management application, and one of the challenges we have with this service that we're trying to overcome is we want to feed every email into it, and that's a lot of transactions, so it would add up too quickly. So we need some way to like filter out before we send to Azure ML these transactions. But basically, you got a usage fee for kind of like a license fee for Studio per user, and they also charge you. It's probably a nominal charge. Frankly, if you run experiments that take a long time, that accumulates up over the month, and you pay $1 an hour. So, if you have a really complicated experiment, yeah, it's going to add up quickly. If you have most normal experiments, you're probably going to pay $1 or $2, maybe $10 a month for that part of it. But then they also charge you for the API usage, a lower fee. Again, for your hourly usage and then per transaction. So if you have something that's taking a long time or something that's hitting it all the time, then they're going to charge you that way. And you can scale it out. There's no charge for the scaling though, so you can scale it out as big as you need to and scale it back down as you need to. So it's somewhat simple, I guess, but I could see where if you had any substantial application, it could get expensive. You're going to pay for those transactions really is where we're going to take the hit.
What advantages does Azure have over AWS and Google BigQuery?
Yeah, I don't consider it necessarily directly comparable to BigQuery because that's kind of like Hadoop in my mind. I know you can do some machine learning scenarios in it. But I think this is useful really to get your models operationalized. I think that's hard to do in other places. You get it integrated with, I'm a developer, so getting it integrated with code is very easy in this environment. That's why I like it. As far as Azure's Amazon's machine learning capabilities, I'm not as familiar with them, but my understanding is that there are more services that you use, not as flexible in terms of programming. So, if you want to do anomaly detection, you use their anomaly detection service. I may be wrong about this a little bit, but it's not as flexible. It doesn't support the hour code and that kind of thing. So you can really build a tailored pipeline for your data right in Azure ML and build a custom model that you need for your application.
Okay, any other questions?
I got one more. So you said all of those are black box, but some of those are like
well known. Yeah.
Yeah, like linear regressions. I mean, it's essentially
Yeah.
it's like the hello world of machine learning.
Yeah.
Is that still black box? Or are they?
Yeah, they don't show you the code for that, but I would bet some money that they're probably using the same kind of algorithm that you're going to have in R and Python. There's no magic pixie dust algorithm by any stretch of the imagination.
My question on that, like, if you wanted to make citable research, and part of this is you're producing reproducible Jupyter research in Jupyter notebooks.
Yeah.
And then if you have like 8 black box modules, and then you want someone to cite your research, and they're like, how did you produce this data?
Right.
That it's
hard.
I get their, that their business model is, but that's kind of a concern to me. Like, well, how do I know, split the data is easy.
Yeah, right.
Copy the data set, but a training model. Wow.
That's a case where if you really want to do reproducible research, you're probably best off using your R code and writing your own scripts. I definitely agree with that.
But it's nice for mocking up. It might still be nice if you have R as like, I'm going to do this, and you can spit together a model really fast.
Yeah.
That's the power of it.
And you can compare and contrast what you came up with and what they came up with, if that adds any value, kind of benchmark.
It might help your resume if you can beat Microsoft in algorithms. I don't know.
What's that?
I said it might help your resume if you can beat Microsoft in algorithms.
Yeah, right. Right. All right, thanks.
Thank you, Chris. We got one more quick one for 5 minutes. Chris Howard is going to discuss very briefly.
Some more of the basically motivation behind managed algorithm deployment. So basically, once you've developed your machine learning model and you have it packaged up and ready to go into numerous different operational systems, how do you deal with it and how do you operate it with native performance? So basically, I'm the CEO of a company that is We'll be releasing technology probably in about a year, so this is a very early preview about what we're up to, but it's all about managed portable algorithms. So basically, we right now, oh, is everything good? Okay, fantastic. So basically, our goal is to be a digital distribution deployment platform for algorithms on native performance that will run on Storm, Spark, MapReduce, and directly onto IoT and embedded systems. So basically, how do you make it so that you're able to create an algorithm once, publish it to a platform, and then run it without modification or maintenance anywhere where it needs to be able to run? And we do that with the following components that you see down there. So really, we are a combination of an API or a contract, like we just discussed, a algorithm distribution management deployment optimization agent that allows those capabilities to make it to the right place at the right time, just in time, based upon what your code requests to the system, as well as the tools necessary to monitor and optimize the operation of those components when they're running. And then lastly, you have a component catalog where you can explore and discover all these components and ideally import them from Azure Marketplace or wherever else you have this code already archived and ready to go for converting from your data analysis environment to an operational system. And one of the unique things that we have in this area is a way to manage and distribute these capabilities in a way where you write something once and you're able to run that component with native performance in the streaming domain, in the batch domain, or directly on mobile, IoT, or embedded devices. And this is being done through more or less a very carefully controlled interface that you more or less get for free when you write to our contract, as well as a lot of services that are designed to bridge these boundaries effectively. So really, once you have your capability working once and it's targeted at the streaming domain, it really is able to run anywhere. And we're right now primarily applying this in the cybersecurity domain, where someone creates a non-trivial detection algorithm for a certain type of attack that's coming in, and you're able to very quickly move it from your analysis environment immediately into your streaming environment, and then move pieces and parts of it directly out to the edge devices that are operating on the edge of your network, so you can start to do your detections with lower and lower latency, with only having to write that core components once without having to redevelop it every time you cross one of those deployment contexts. And that creates very interesting possibilities, especially when you get to larger scale things. But why would you want to be able to do this? A lot of people are doing this by hand just fine with no problems, no issues. And this really comes out of the large scale defense-oriented problems that this was designed for. So really, fundamentally, when you look at a distributed sensor processing system, you've got processing on each sensor, you've got processing on the data relay, processing at the ground link terminal, processing at the remote users, and maybe processing at a national or regional ops center. So really, when you're dealing with this complicated of a processing topology to make it so the right data makes it to the right person at the right time, how do you deploy your capabilities to it in a way that you can react in seconds when something interesting happens, as opposed to traditionally the months that it takes to develop a new capability, regression test it, and get all the permission to get it into the right systems at the right time. So really, how do you adapt sensor processing in response to world events so you can respond in seconds as opposed to months? How do you maximize intelligence with limited or denied networks, really, and that comes into play really with all the big data applications, especially in the Internet of Things domains where you've got sensors like your cell phone that's able to, like the camera on your cell phone is able to produce data at like 400 or 500 megabytes a second, but by the time it's stored on your phone, it's maybe 20 megabytes a second, and by the time it goes out to Twitter, it's a few kilobytes per second, and there's an awful lot of data that's lost in that process, because there's no way in heck you're getting it over your cell phone networks. In fact, you're not going to be able to do that anywhere in the near future. And I can tell you there's a lot of really interesting things in that data that's being thrown away, that's currently being taken off those sensors. And you want to be able, and to take advantage of that, you have to push as much of that processing as close to where the data being generated as possible. But that processing and what you want to extract out of the data is constantly changing. So how do you manage that system? And that's a huge challenge that has yet to be really addressed, except for building a whole bunch of custom code yourself to optimize your particular system. And then, again, how do you reduce the time to test and deploy new capabilities, or very easily do like 1 million A/B tests on your data that's coming in to optimize what you actually be able to run and to extract the signal out of the noise that you're collecting across one or more sensor platforms that you have out there. And then the next step is how do you properly take all that information I just talked about and make it so you can automate what you want to automate, what's running at any given point in time to optimize for the amount of CPU, memory, network, or even just about your high-level goals of the system of what you're actually trying to accomplish at any given minute. And again, it's easy with the current IoT devices and the current systems because they assume that you're only doing one thing at a time, take your Nest thermostat. But if all of a sudden you wanted to do something different with that Nest thermostat and do that in a way that you could, change the way that the system operates in minutes to look at something else, such as you've got a weird temperature spike, I now need to look at other sensors to understand what this data is actually trying to do, or try to add that to maybe your thermostat with your fire alarm, or do other things to try to get extra information in the system. How do you, as an analyst, respond fast enough to do something interesting to that system? Or if you just have weird data, tag that data for offline analysis later for your traditional data science application. So really, that's the kind of automation challenge that we're talking about, and it's really non-trivial because you want to make this as automated as possible, because you're never going to be able to do everything at all times, especially when you get into more of an IoT processing context of data everywhere all the time, as opposed to the very nice way we're able to do most of our data science these days and co-locate all that data on a single data center or a single cloud. Instead, the data is going to be everywhere, and you're never going to be able to co-locate that data. So how do you make it so you look at the data where it exists at the appropriate fidelity for whatever your information you're trying to extract at a given point in time? It's a humongous challenge that is very poorly addressed, except in places where they kind of hack in the capabilities with billions of dollars of development for very point-specific problems. So anyway, fundamentally, just like we saw in the last Azure ML situation, this is really how people want to operate. They want to be able to have a single platform where you can have a whole bunch of capabilities pickled up and be able to throw them at the right place at the right time, with analysts being in the middle of the situation so that they can immediately have alerts that interesting things are happening, and when they have an alert that something's interesting to happen, be able to pull the appropriate capabilities out of the catalog, assemble it into an operational capability package, and deploy it out to wherever that information needs to be processed or be analyzed in greater detail. So really trying to create it so you have a single touch point for all these activities and these algorithms on a number of different platforms in a way that makes it so you only have to deal with one system at any given point in time, even though that system may touch 100 or more disparate individual systems. So when we're currently looking at applying this into cybersecurity space, and I won't go into too much details about that, but really you can start to use this kind of architecture and system to start to help bridge your threat analysis systems with your threat intelligence systems and your security platform, so that you no longer are stuck in an individual silo for a single capability, or only stuck dealing with these kind of problems like in a single node. So for example, for a cyber problem, you want to run some of your detections actually within the Cisco switch, some of it actually at the telco location, some of it in your traditional defense environment, say your FireEye or your Norse or your Proofpoint or whatever, and then be able to quickly bridge those capabilities into your traditional analysis environment. So basically collect a whole bunch of data, throw it into a database, say ArcSight, do static analysis against in your batch environment, then very quickly throw that cybersecurity detection, mitigation, and response into your streaming environment, and then again throw it into your edge device, or even throw it out further to the telco, or if you're the government, maybe even on the attacker himself. So who knows? There's a lot of really interesting use cases you can come up with this kind of thing. So anyway, basically right now you can think of us as like a cybersecurity catalog. We have an interesting draft project out there that demonstrates this capability actually working in production type workflows for like a catalog, integration tools, and code snippets, as well as integration into limited type deployment environments. And like I said before, right now we work with Java algorithms in Storm, Spark, and MapReduce, but our interfaces and concepts will easily extend into pretty much C, C++ code and anything else you might want to be able to use it with down the road. But right now we're targeted at big data environments because that's where the immediate term use cases are for what we're doing. So I tried to make that quick, and I think I was. So anyway, hopefully that was interesting to people. And if anyone's interested in digging in or trying to utilize this stuff in the near term, feel free to let me know. Any questions? Yeah, go ahead.
One I'll ask and one you don't have to answer, but what's your background and what's the business case or the revenue model?
Well, it depends upon the industry you're trying to throw it at. My background actually comes from DoD type processing of distributed sensor systems, and this is more or less a response to how to do it right and how to do it basically take problems that traditionally took applying the processes, trying to take the best of breed analysis processes that are currently utilized in that space, combined with the realities of the systems and the integration challenges they have in that space, and try to put it all together in a way that both works for that traditional government market, which is one of the markets that we're targeting with this, as well as make it so the same exact principles and code will apply to both big data markets as well as sensor meshes powered by IoT type devices.
And had you done market analysis on, did you go meet with people and ask them what they want, or is this you were in the space and saw a gap?
Well, we were in the space and saw a gap, and right now our near-term focus is actually on cyber type applications, mostly because that's where there's the current interest. And that's where we also see, we're also working with customers in the space to develop out some early demonstrator capabilities that shows that this analysis approach is better than some of the traditional ways of doing things, particularly once an organization has grown past the needs of a single vendor solution and it also needs to bridge like 5 or 10 vendors in order to get their full solution. So. Yeah, go ahead. Yeah.
So are you crowdsourcing algorithms, or is it crowdsourcing from that community?
Mostly we're crowdsourcing from
leveraging that particular, you're leveraging those number of human minds, and so no one entity is tasked with all that algorithmic development.
Well, yes, our goal is to make it so you can share easily across those boundaries, but initially it's mostly helping organizations internally help deal with some of the infrastructure understanding they have internally. But the broader view is that once we have demonstrate success in 1 or 2 of those places, we've got a number of interested university partners who want to start utilizing this to help make it so that developers, once they get something developed and mature, have a mechanism to actually get it out to the market and distribute it out to a number of different parties as opposed to in a supported, managed way.
Is there like a part of the revenue model that says it's crowdsourced, but you can sell your algorithms?
Yes, we have that built into the
person that uses your algorithm, or each time they use, is that part?
Yeah, that's kind of built into the catalog portion of it, where you can either give your capabilities out for free, or there's ways that you can do chargeback and usage tracking, so that you can do those multiple, so you can utilize those different models. So. Yeah, that's not built yet, but that's kind of the large scale on how you create a centralized catalog that can be shared by a broad community, either across an organization or across multiple industries, to start to get some of these capabilities more out there. And I'm being careful when I say the word algorithm, because when I say algorithm, I'm talking about like a finished product that has a known input with a desired output, and it's more like a finished data science product is kind of what you put into this, not a and into that you'd have a whole series of internal processing that that do the data science for you. This is really the goal, is to distribute like 80% finished products with and be able to get those 80% finished products wherever they need to run, and then provide the ability to connect those 80% capabilities with the people and resources necessary to fill that last 20% gap to do the last minute tuning and tweaking for the local anomalies that show up in data.
How do you define managed algorithm platform?
Well, more or less how I'm defining it. Well, the way I managed it, basically we have the algorithms, we have the interface, the contract associated with it, and we have the interfaces necessary to manage and track the deployment of those capabilities. Also included of that, of course, is data rights management and authorized execution of those components when those levels of protections are appropriate. So by managed, I mean you have a good idea of what, if you're a developer of a component, you always will have a good idea of what's being run where for what reasons. Or if you're trying to manage a cluster of devices, you have a good idea of what's running where for what reasons. So the data visibility really depends upon what's appropriate for that execution domain. But by managed, I mean by, yeah, you're able to develop something once and easily get it distributed out. So
it's interface management across hardware and like operating systems.
yes. Mm-hmm.
Or database models.
Yeah, and we do have.
That seems pretty big.
Yeah, it's a heck of a challenge. This is like the most ambitious startup I've heard of in a long time.
It's ambitious, yes, it's hard, but we've already demonstrated the ability to develop capabilities once and run it on Storm Spark and MapReduce. Same capability, all different places, basically right across the Java domain. We do have the C++ stuff is much harder problem, so we don't expect to get to that for a while, but we have an approach that we know that has a good likelihood of working, and thanks to Apple for fixing some of the core LLVM problems for us.
Have you created any investor pitches or pitched any investors?
Yes, we have.
How'd it go? Or should I not ask?
I'm perfectly open.
Sure that
We
there's a lot
currently
of people.
have investor interest in a number of parties. We actually have a much more targeted pitch that we've been using that's solely in the cybersecurity space. It doesn't talk about a lot of the lower level implementation details that I talked about right now, because really at the end of the day, when you talk cybersecurity, people just want something that works. They don't care about how it works, they just want it to work. So
You'll probably get bought by a defense contractor in a couple of years when you deploy a functioning product.
yeah, so
That might be part of the plan.
that's part of that's part of it. We've been talking to some of them.
How many software developers do you have? I mean, this is such a daunting challenge. It's like eating an elephant, I guess. But I mean, how many software people do you have on your team, like right now?
Right now, primarily we have 3 full-time developers and myself and my co-founder.
Wow.
We're still early on in the process, but this is a concept that actually escaped a former defense contractor, and we're basically running with it with their permission. So that's kind of what it's coming out of. So it's a pretty well-baked idea. It's just trying to figure out how to get the proper commercial traction. So
What's the target market?
the initial target market is mostly going to be enterprises or who have large-scale algorithm integration issues right now. So basically how you quickly move, develop capabilities between execution tiers. And that's kind of...
Can you give us an example and how you envision, the Kursplotty product to solve their specific problem?
Oh, sure. Let's just say that you have a, let's see, I'm trying to figure out a domain. Okay, so let's say you have I'm just going to go with the security domain because that's an easy one that is quite common. And suppose you have a type of detection that requires something more complicated than pattern matching. So to do that, what you do, and I think I talked to this use case before, but to do that, basically you'd want to be able to go in and, assuming that you've already archived all your packets in some sort of analysis environment, basically how you utilize our platform is that you'd basically be able to look at all the, okay, I'm trying to go back and, but against that data, you have analysts that would develop lots of different types of analysis to detect various different types of anomalies across the system as you go through the data science process. So the goal is to build like a catalog of components for both machine learning primitives that can be distributed across your sensor network, as well as detections that you'd be able to utilize to understand and react to and notify you when interesting things occur when certain type of events happen, such as certain packet sequences that represent certain type of sequences, or being able to build your correct type of reaction approaches when, for example, a FireEye device detects a certain type of event happening correlated with your threat protection system, and be able to present that information to an analyst who can then go through and do the historical analysis to understand whether or not that's occurred or not, and develop a component that, and then if that can result in some sort of algorithm that can detect that type of event that you were alerted that might be occurring, you can then quickly distribute it out to your streaming environments on all the packets that are coming into your network, as well as potentially your edge devices or your network switches to determine whether things are happening there. So right now...
So piggybacking on the finance presentation, you're kind of like taking all the hedge funds and combining all their crap into a cohesive community to watch for correlations or pattern matching or whatever the algorithms. But they've got algorithms that they've tweaked, and then they recycle them, which is really, God, you gotta love having that algorithm.
Yeah.
How are you porting all this to all the different, I mean, you're saying you're porting it to like edge devices, like write once, native performance everywhere. I mean, that's,
well,
how do you...
We're cheating right now because we're right now pure Java. So However, we do have an approach that we've been developing that probably won't be operational for a while, that is using what should be deployable to anything that's 64-bit Linux based, utilizing some of the recent advancements in being able to do intermediate compilation. So it's look up how Apple was doing bitcode for iOS 9 applications and doing the modular on-demand code deployment strategies for iOS 9 applications, and our goal is to piggyback on a lot of that work that's going on there. And they're already doing intermediate compilation of every new app that's going to the Apple Store. And you're actually able to create individual modulars that apps can download on demand, and then your code will automatically be cross-compiled to whatever iOS device that you're operating on for various different processor architectures. So it's like ARM7, ARM9, whatever. So single core, multi-core. So that's kind of our approach to getting into the C, C++ space and some of the more performance optimized space. But right now, we're mostly working with any system that's running a full Java stack, and we should be able to work with systems that are working with more of an embedded mobile Java stack maybe sooner, but I don't think I think there's some API compatibility issues there. So we're really targeting anyone who can really run a full up VM machine right now. But that's because we're optimizing against Storm, Spark, MapReduce in the big data world, because that's what people want to use today. And that's what a lot of stuff runs on, so it's a good starting point.
Oh yeah, so you're talking about sort of crowdsourcing these algorithms. Are you worried about any liability that sort of comes? So let's say that I wasn't a genius, but I put something out there and it looked passable, and then somebody made some terrible mistake and it cost them a lot of money. Is there anything that you have against this, or is this kind of like, user beware and make sure to split your data and actually run test cases?
That's the goal. The goal is to make it so that the person who's downloading, executing the code, it's their job to properly test and execute things appropriately to verify there's nothing malicious mixed in with this. Now, when we do deploy things, we do have sandboxing and other stuff involved, so at least if someone's doing something nefarious, it's only against the data stream, not the system as a whole. So.
Well, actually, that's a great question, because there'll definitely be accidents as well as intentional malicious.
Yes, and that's why
I didn't mean intentional maliciousness.
No,
I meant something that looks right, but then when you use it,
Unintended consequences.
Yeah, I thought I was doing it right, but
accidents will happen.
And that comes down to appropriate certifications and having to bring in external review into things that have various different trust levels.
You better get a good insurance policy.
Yes, or figure out ways to be sure that it's third-party liability for code that you bring in through external sources.
Yeah, thank you. Thank you, everybody, for coming. We're going to get kicked out of here at 6:30, so I'm going to have to ask everybody to leave. Thank you so much. It was great meeting you all. I learned a tremendous amount, and I hope you got a lot out of it. Thank you for coming.